Today I'm going to be exploring the topic of integration and going through some basic examples to just help us on our way to actually being able to realise what it is and what is the actual reason for it. So, if we started off with a function, previously we have looked at how we could differentiate a function. So if I have a function of f of x, let's call it 5x cubed, we could differentiate that function. Because it's of the form x to the n, when we differentiate it, we do these two steps. We multiply by the power, so we times by the power, and then we subtract 1 from the power. And that would give us our gradient function, so our f dash of x, which in this case would be 15x squared. So if I want to think about the opposite of this, or the inverse, what we are doing is called integration. Sometimes it's known as anti-differentiation, which is what it is in this case. However, it's just like a function machine where we have to do the opposite steps. So instead of subtracting 1 to the power, I have to add 1 to the power. And instead of multiplying by the power, I'm going to be dividing by the power. This is great for this scenario because 15x squared, when I add 1 to the power, is 15x cubed. When I divide by the power is 5x cubed, which is what I need. However, there comes some complications with this. If I was to think about the graph 5x cubed plus 10, when I differentiate this, I would end up with 15x squared, which is what I want, because it is the gradient function. However, when I go back to integrate it, I just end up with 5x cubed. I don't get this plus 10. And the reason for that is because if we think about the graph, the plus 10 actually has no input on what the gradient would be. It has no bearing on the gradient function. It's just a vertical translation of 10 units. So how do we combat this in integration? Well, if we're not given points that we could substitute in, what we must do is, once we integrate it, so let's say we've integrated our function of 15x squared, and we get a function of f of x as 5x cubed, we need to add on some constant of integration, and we just call that the value c. So that is a constant of integration. So let's try and put this into practice. I've got some questions here which I'm going to go through. I'd like you to write them down first of all, so that you can make notes as I go through them. But the first question is find y when, and then we've got dy by dx equals 4x cubed. So thinking about my rules, my y is going to be equal to, well, x cubed add 1 is x to the 4. Then divide by the power, 4 divided by 4 is 1, so it's just y equals x to the 4. Once I've done that, I need to add on my constant of integration, because this is something called a definite integral. So we would actually just write this as y equals x to the 4 plus c. For the next question, I've got x to the 5. The way I would write this is y equals, I would always add 1 to the power and just write it down. And now I'm going to divide by the power. Well, dividing by 6 is just going to be a 6th lot of x to the 6, and then again plus c. And lastly, 3x to the half, what I'm going to do is again write down my power straight away. Well, adding 1 is going to be to the power 3 over 2, and then I'm going to divide by 3 over 2. Now we should know that when we're multiplying fractions, when we're dividing fractions, we can multiply by the reciprocal. So a over b divided by c over d is the same as a over b multiplied by d over c. So I'm going to use that knowledge for this scenario. So I'm going to multiply this by 3, because that's my coefficient of x, and then multiply it by 2/3. And it's going to be plus c. So therefore, for this scenario, I'm going to get y equals 2 lots of x to the power of 3 over 2. So, what I'd like you to have a go at are some questions here. I want you to think carefully about what your answers would be. And now I'm just going to go through them. So if we're given a differential of 2x plus 7, my integral of f of x Well, I'm going to add 1 to the power, so it's going to be 2x squared, divided by 2 is going to give me x squared, plus, now, as we have a constant, if we were thinking what would differentiate to give us 7, then it would have to be 7x, or the way you could think about this is x to the 0, so therefore we add 1 to make it x to the 1, and dividing by 1 will keep it the same. And again, we need our constant of integration. So I'm just going to start writing down the answers for the next few questions. So this is a third x cubed subtract x plus c. In order to answer this question, the first thing I want to do is rewrite this as a form of something x to the power of n. So therefore I'm going to change this x to the 7 as to being 2 lots of x to the negative 7. 2 lots of x to the negative 7. And then I can integrate this nicely by adding 1 to the power to make it negative 6 and dividing, so I get 2 over negative 6 x to the negative 6, which is obviously going to be negative a third x to the negative 6. Likewise with this one, I want it of the form x to the n, so I'm going to rewrite this as x to the power of a third, and then when I come to integrate it, I'm going to get x to the power of 4 over 3. When I'm dividing again by a fraction, I'm going to multiply by the reciprocal, so it's 3/4 of x to the power of 4 over 3 plus c, thank you for reminding me, and for the bottom one we're going to include every step that we've done so far. So, the first thing I look at is my power. I'm going to add 1 to it to make it 11 over 6. Then I'm going to multiply by the reciprocal, so I'm going to multiply the 33 by the 6 over 11, and what we should notice is that 11 and 33 is going to cancel down to 3, so therefore we get f of x to be equal to, well, 3 times 6 is 18, lots of x to the power of 11 over 6. So this was just an introduction to integration. In the next session we're going to explore it a little bit further and see what are the uses and properties and maybe go through some exam style questions. I hope you enjoyed and I hope you had a go at these questions. Please go back if you made any mistakes and check and see if you can find where you went wrong, and I'll see you in the next session. Thank you very much.